had asymptotes. And so we are going to find us some asymptotes here. Remember, this type had both, usually had both a vertical and a horizontal asymptote. So let's review that. How do I find for this one the vertical asymptote? Well, remember, the vertical asymptote occurred where you had an undefined expression. And so when you want to find the vertical asymptote of this, you set the denominator equal to 0. 2x plus 3 equals 0 will be, the solution to that will be the vertical asymptote. Subtract 3, divide by 2. Negative 3/2 is the vertical asymptote. And what I'm going to do then on the graph, that's negative 1.5. I'm going to draw a vertical dotted line at negative 1.5. My vertical asymptote. Okay? What about the horizontal? Well, the way we did that, remember, is basically we just divided. We did y equals a over b, where a and b are the leading terms, where the terms match degrees. So in this case, the horizontal asymptote is going to be, well, the leading terms here, you got 5x over 2x, right? 5/2. Y equals a over b is the horizontal asymptote. 5 over 2. Or 2.5. So at 2.5, I've got a horizontal. So I'll draw a horizontal dotted line at 2.5. Okay? All right, then what we did, for the intercepts, the y-intercept, well, that's same old, same old. The y-intercept, you set x to be 0. So you got 5 times 0 is 0. Minus 7 over 2 times 0 is 0 plus 3. That's negative 7 over 3. So it's going to cross the y-axis at negative 2 1/3. The x-intercept, again, the same old, same old. You set, for the x-intercept, you set y to be 0. And then the thing about that is, you multiply both sides by 2x plus 3. What do you get? What happens? Yeah, we solved that. We multiply both sides by 2x plus 3 to clear out the 2x plus 3. Well, 0 times 2x plus 3 is 0. 2x plus 3 cancels, so you just wind up with 0 equals 5x minus 7. And if you solve that, add 7 and divide by 5, you got 7/5 is the x-intercept. Or 1 2/5. So it's going to cross the axis at 1 2/5. Okay? Well, that gives us some information to go on, but remember the other thing is we did a little table here with values around the vertical asymptote. Do a nice little table here, x and y values, and I'm just going to get a couple of values around that x vertical asymptote. What is it? Negative 1.5. So let's do negative 2, negative 3. Let's do negative 3, then negative 2, and then negative 1. Those are just values around my vertical asymptote. And so what we get, if we plug in x to be negative 3, we get what? Negative 15 minus 7 over negative 6 plus 3, which is negative 22, over negative 3. Negative 22 over negative 3, if you can't read that, is 7.33. At x is negative 2, well, if I plug in negative 2 for the x, I'll have negative 10 over minus 7 over negative 4 minus 3, plus 3, which is negative 17 over negative 1, which is positive 17. Okay? And then if x is negative 1, I have negative 5 minus 7 over negative 2 plus 3, which is negative 12 over a positive 1, which is negative 12. So what those points do is give me some nice little points. At negative 3, I'm at 7.33. So at negative 3, 7.33. At negative 2, I'm way up here at 17. And then at negative 1, I'm at negative 12. Because remember, what happened is, on these rational functions, is the vertical asymptote divides it up into two parts of the graph. Okay, well, on the left part of the graph, if I connect these two, remember the vertical asymptote either goes upwards towards your vertical asymptote or downwards. It never crosses the vertical asymptote. Well, if these 2 points have anything to do with it, it looks like it's headed upwards, doesn't it? And then remember, on the horizontal asymptote, what does that tell me? The horizontal asymptote tells me where the graph levels off on the ends. So this graph is going to level off as we go out towards the ends at that horizontal asymptote. Okay? Now on the other part, these 3 are on the other part. So it looks like the graph's headed down towards that vertical asymptote on that side, and then it comes up and levels off at the horizontal asymptote. Okay? Remember those? All right. Those are fun ones. Another thing we talked about on number 8, we talked about some logarithms. And should be able to evaluate logarithms here. And in this case, what have I got? Logarithm base 2. Yeah, if you say that equals something, then remember the definition says 2 to the something equals 1 over 2048. So I need to come up with a power of 2 that equals 1 over 2048. Well, if you try powers of 2, you got 2 to the 10th. It's way on up there. 2 to the 10th is 1024. So 2 to the 11th is 2048. However, I want 1 over 2048. So what is the power I need here of the 2? Need negative 11, don't I? Yeah, to get it to be flipped over, 1 over 2048, it needs to be 2 to the negative 11. So the logarithm evaluates here to be negative 11. Now on B, we want 3 to what power is negative 81. What about that? Yeah, can't do that. Not a real number. Yeah, if you have the log of a negative or anything such as that, you can't do those as a real number. Okay? All right. What about solving 9a as solve a logarithm equation? Well, the first part reminds us of some properties. To get this thing solved, don't I need to combine logarithms? And when I combine two logarithms that are added together, what happens to their inside parts? They get multiplied. So I'm going to do log base 2 of x minus 6 times x equals 4. Yeah. If you have two logarithms that are added, you can combine them by multiplying the inside parts. If they're subtracted, you divide the inside parts. But this one is added, so we multiply. So that'd be log base 2 of x squared minus 6x if you multiply that out together. Then to actually solve a logarithm equation, remember we did the exponentiate thing. We've got a base of 2, so I'm going to exponentiate both sides to base 2, meaning I'm going to go 2 to the log base 2 of x squared minus 6x equals 2 to the 4. That's exponentiate both sides to base 2. The reason I do that is because what happens on the left here? Well, the 2 and the log base 2 cancel out. And it just leaves me x squared minus 6x, and then the right side is 16. Yeah, so now I've got a nice x squared equation. Make one side 0 and factor. Probably do that a lot on the final there. Move the 16 over, make one side 0 and factor. X and x, 16 minus 8 and 2. So that would be x minus 8 equals 0, so it would be x equals 8. X plus 2, so that gives me x equals negative 2. However, what about it? Both of them work? One of them doesn't work. Why not negative 2? Yeah, if you plug in negative 2 up in your original equation, that would give you the log of a negative number. So we don't want that, so it looks like 8. 8 is it. All right, now, 9b. 9b is an exponential. How do we solve those? Got an x and the exponent. Well, the idea is to get the x out of the exponent somehow or another. In this case, here's what I'm going to do. First of all, I'm going to get the exponential part by itself, so I'm going to subtract 5, both sides. So that would be 2 to the 3x equals 25. Then to get the exponential, the exponent, the x out of the exponent, remember what I do then? Well, it's going to use another property of logarithms. I'm going to do a logarithm here, natural log both sides. Because unlike in the previous step, what can I do in this step? Well, since it's a logarithm now, can I bring the power out front? Yeah, I can do that in logarithms. Can't do that otherwise. So I'll wind up with 3x ln of 2 equals ln of 25. And so then all I have to do, one more step here, is divide off the 3 and the ln of 2. So I have ln of 25 divided by 3 ln of 2. And the only thing is, it's the x by itself, the only thing is when you put that in your calculator, be sure to put parentheses around. Since you've got two things in the bottom, put the parentheses around the 3 and the ln of 2. So we've got ln of 25 divided by parentheses 3 ln 2. And I get 1.548. Is that okay? All right. Last but not least page. Okay, number 10. Graph 3 to the x plus 1 minus 5. Yes, we talked about these earlier. This is an exponential function because x is in the exponent. And the graphs of those, well, basically we called them hockey sticks. But, yeah, you've got a kind of a hockey stick. Now, you actually have two possible. Sometimes you have those, and then sometimes you have those. How do I know which one is which? Well, this one is if the x is positive, if you have a to the x. And this is if you have y equals a to the minus x, right? In this case, I've got the first, right? 3 to the x plus 1, not 3 to the minus x. So I'm expecting one of these. Now, the other thing here is this is an asymptote, and it starts at 0, but in this case, the asymptote has been shifted because of this, right? Isn't that going to shift it down 5? So the horizontal asymptote is now not 0, but y equals negative 5. So that's one thing I could probably go ahead and put in. At negative 5, let's put in the horizontal asymptote. Okay? Now the other thing, this shift, talking about shifts anyway, we know it's going down 5. That plus 1 makes it go 1 which way? 1 to the left, yeah. So that's going to shift everything 1 to the left, just in case we're asked about that. Yeah, remember that's plus 1 with the x. That makes it go to the left. The minus 5 on the outside makes it go down 5. So anyway, The other things we did, yeah, on these we did put a little table together. Since it's 1 to the left, yeah, we might go negative 2, negative 1, 0, 1, and 2. See what happens there. Well, if x is negative 2, that would be 3 to the negative 2 plus 1 is negative 1 minus 5. That's 1/3 minus 5. That is negative 4 2/3, or negative 4.666. At x is negative 1, that would be 3 to the negative 1 plus 1 would be 0. So that would be 1 minus 5. That's negative 4. At x is 0, we'll have 3 to the 1 minus 5. That's 3 minus 5, which is negative 2. At x is 1, we have 3 squared minus 5. That's 9 minus 5. That's 4. And at 2, we have 3 to the 3rd minus 5. 27 minus 5 is 22. That's my table, looks like, anyway. All right, so at negative 2, I'm at negative 4 2/3. At negative 1, I'm at negative 4. At 0, I'm at negative 2. At 1, I'm at 4. And then at 2, I'm at 22. Yeah, so there's my hockey stick. Okay? All right. On the next one. I don't know what happened to my number there, but that should be a 10. All right, number 11. Sketch the graph of a logarithm. Well, on a logarithm, it goes the opposite way of an exponential, kind of the reverse or the inverse of it. Logarithms look like that. And so logarithms have the vertical asymptote, and this one's not shifted. If there's a shift, right or left, it moves. But in this case, there's no shift on it, right? So the vertical asymptote is just still at x equals 0. Your logarithms have a vertical asymptote, and in this case, it is at x equals 0. All right. Now, for a table, remember, since this is base 5, what I might want to do for the x's is choose out base 5 numbers, and I'll start with 1, x is 1, but then do base 5, like 5, and then 25. And that's because the base is 5. Do powers of 5. If the base was 2, I do powers of 2. If the base was 3, powers of 3. Okay? This is base 5, so do powers of 5. Yeah, you got log then, if x is 1, you have log base 5 of 1. Well, that's saying 5 to what power is 1? That would be 0. If x is 5, I have log base 5 of 5 is what? Well, that's 5 to what power is 5? That would be 1. And then log base 5 of 25, same thing. That's 5 to what power is 25? That's 2. So I've got 1, 0, 5, 1, and 25, 2. Yeah, so there you go. There's your shape. And then again, remember, you got a vertical asymptote there at x equals 0. Okay? All right, then. Last but not least. Sketch the graph. All right, so this is an x cubed graph. We looked at those. What we started with on x cubed or x to the 4th graph, we started with the end behavior. Remember, on x cubed graph, they alternate. One's up, one's down. On the x to the 4th ones, they either go both up or both down. This is an x cubed, so one's up, one's down. Now, since it's a negative x cubed, which one's up, which one's down? The left up, or is the right up? Left's up, the right's down. Yeah, for a negative x cubed, the left is up, left end's up, the right end's down. And so on the graph, yeah, the left's going to be up, the right end's going to be down, just to kind of indicate that. That's what happens on the ends. Now the other thing to go off of here, well, the y-intercept, you always want to see what it is, but in this case, 0 minus 0 plus 0 is 0. So we've got a y-intercept of 0. Some better points here that will help us are the x-intercepts. Set y to be 0, or f of x to be 0. And since that x cubed term is negative, and we've got it equal to 0, I'd switch sides with all those. Add x cubed, add x squared, and subtract 6x, because then it's a little bit easier to factor. Factor off an x, so I have an x times x squared plus x minus 6, and then factor the x squared plus x minus 6. That'd be x and x, positive 3 and negative 2. So wind up with x-intercepts. That'd be x is 0, negative 3, and positive 2 would be the x-intercepts. All right, then recall what we did was another little table here. And on the table, we're going to do x values between x-intercepts. So I've got x-intercept here. I've got negative 3 and 0, so I'm going to do a negative 2. I've got x-intercept 0 and 2, so I'm going to do a positive 1. Do x values between those. So if x is negative 2, then I have negative 2 cubed minus negative 2 squared plus 6 times negative 2. So that's going to be negative 8 minus positive 4 minus 12. So that's 8 minus 4 minus 12. Hey, that's a negative 8, isn't it? Is that right? Then if x is 1, I'll have negative 1 cubed, negative 1, and then negative 1 squared is negative 1, and then plus 6 times 1 is 6. Hey, that's positive 4. So when x is 1, y is positive 4. So that gives me two other points to shoot at here. So we got negative 2, negative 8. Whoop, negative 2, negative 8. Go here. And then at 1, I'm at 4. So I know my ends, so I've got